Imagine a world where we could harness pressure, store it like a battery, and use it on demand. Does it seem like a far-fetched idea? Well, it's not. Welcome to the concept of compressed air energy storage, or CAS. This ingenious method allows us to store energy generated at one time for use at another, using nothing more than compressed air. Think of it as a giant, high-pressure battery, but instead of chemicals, it uses the power of air under pressure. At a utility scale, this can help balance our energy grid, storing excess energy during periods of low demand and releasing it when demand peaks. By understanding CAES, we step into a future where energy storage becomes more efficient and sustainable. And while the technology is still evolving, the possibilities it offers are truly electrifying. So, let's dive deeper and see how this all works, shall we? So, how does CAES work? Let's break it down into 3 steps: compression, storage, and release. First up, compression. During periods of low energy demand, electricity is used to squeeze air into a smaller volume. This process, akin to inflating a bicycle tire, generates heat. Now, this isn't just air getting a bit warm, we're talking about serious heat, the kind that can be harnessed and used in the next stages of the process. This is the first step in transforming electrical energy into potential energy. Next, we move on to storage. The hot, compressed air is stored under high pressure in a storage container. These containers could be anything from underground caverns to above-ground tanks. The key here is that the air is kept under high pressure. This is important because the higher the pressure, the more potential energy is stored. It's like a fully wound spring, ready to unleash its energy when required. Finally, the grand finale, release. When demand for electricity peaks, the stored compressed air is let loose. As it expands, it drives a turbine. Now, turbines are fantastic pieces of kit. They convert the kinetic energy of the expanding air into mechanical energy, which is then converted into electrical energy. In essence, the process of compressed air energy storage is a dance between different forms of energy. Electrical energy is converted into potential energy during compression and storage, and then back into electrical energy upon release. The beauty of this system is its simplicity and versatility. It's a way of storing energy that doesn't rely on specific weather conditions like solar or wind power, and it can be scaled up or down depending on the demand. But it's not just about the size of the system, it's also about when it's used. By storing energy during times of low demand and releasing it during peak periods, CAES can help balance the grid, ensuring that electricity is always available when it's needed most. So, it's quite simple, isn't it? Compress air during low demand, store it, and then release it when the demand peaks. There are different types of CAES systems. They are adiabatic, diabatic, and isothermal. Each has its own unique features. Let's start with the adiabatic system. This is a smart system that doesn't waste the heat generated during compression. Instead, it stores it and uses it during the expansion phase. This clever use of thermal energy aims for higher efficiency, making the adiabatic system a fascinating option. However, it's important to note that this system is still in the development stages and is not yet commonplace. Next, we have the diabatic system. Unlike its adiabatic cousin, the diabatic system releases the heat generated during compression into the atmosphere. While this might seem like a waste, it's a simpler, more straightforward approach, which is why it's the most common type of CAES system in use today. However, its efficiency is lower compared to the adiabatic system. Lastly, we come to the isothermal system. This system attempts to maintain a constant temperature during both compression and expansion. It's a very ambitious approach, aiming to achieve maximum efficiency by minimizing energy loss through heat. But it's also the most complex and challenging to implement, as it requires advanced heat exchange technologies. Each of these systems has its own strengths and potential applications. The adiabatic system, with its focus on efficiency, could be ideal for large-scale utility storage. The diabatic system, being simpler and currently more common, is suitable for a range of applications, including grid balancing. And the isothermal system, though still largely theoretical and challenging to implement, could revolutionize energy storage with its high efficiency, if the technological hurdles can be overcome. So, there you have it. 3 different approaches to compressed air energy storage, each with its own unique features and potential applications. Whether it's the efficiency-focused adiabatic, the simpler diabatic, or the ambitious isothermal, CAES systems offer a fascinating glimpse into the future of energy storage. These variations in CAES systems offer flexibility and adaptability in energy storage. Now, let's imagine a future where compressed air energy storage technology is advanced and widely implemented. The impact on how we use energy could be significant. Picture this. Renewable energy sources like wind and solar are intermittently producing more power than we need. Instead of wasting this excess energy, we could use CAES to store it. When the wind stops blowing or the sun sets, we could then tap into this stored energy to keep our lights on and our devices powered, making the renewable energy sector more reliable and efficient. Then, think about the stability of our power grid. It's a delicate balancing act, matching energy supply with demand. CAES could act as a buffer, storing energy when demand is low and releasing it when demand peaks. This could prevent outages, reduce the need for costly peak-time power plants, and create a more resilient power grid. But the potential of CAES doesn't stop at the power grid. Imagine vehicles powered by compressed air. While we're still a long way from seeing this become a reality, the concept offers a tantalizing alternative to fossil fuels and batteries. Cars, trucks, and even trains could run on air, reducing our reliance on non-renewable energy sources and decreasing carbon emissions. And let's not forget about industrial applications. Many industries require high-pressure air for their processes. Stored compressed air could provide a ready supply, reducing energy costs and carbon footprints. It could revolutionize industries from manufacturing to mining, creating more sustainable and efficient operations. In this hypothetical future, CAES could also play a key role in tackling one of the greatest challenges of our time, climate change. By allowing us to store and use renewable energy more effectively, CAES could help us reduce our greenhouse gas emissions and move towards a cleaner, greener future. All these applications paint an exciting picture of a future where CAES is an integral part of our energy landscape. It's a future where we harness the power of pressure, store it like a battery, and use it when we need it. In this future, compressed air energy storage could be a game changer, making energy use more efficient and sustainable. However, like any technology, compressed air energy storage, or CAES, comes with its own set of challenges and considerations. First, there's the question of efficiency. Current systems lose a significant amount of energy due to heat generation during the compression process. This heat loss reduces the overall efficiency of the system, making it a crucial area for potential improvement. Next, we have the cost. The infrastructure required for CAES, like underground storage facilities, can be quite expensive to develop. This financial barrier could limit the widespread adoption of the technology, especially in regions with scarce resources. Lastly, we must consider the environmental impact. While CAES is indeed cleaner than fossil fuels, the construction and operation of large-scale storage facilities could potentially affect local ecosystems. Therefore, thorough environmental assessments are necessary before implementing these systems. Addressing these challenges is crucial to the successful implementation of CAES. So, storing pressure for later use is not only feasible but also in practice to some extent with compressed air energy storage, or CAES. We've seen how CAES works, compressing air during periods of low energy demand and releasing it during peak periods. We've explored the different types of CAES systems: adiabatic, diabatic, and isothermal, each with its own unique approach to handling heat during compression and expansion. We've envisioned a future where CAES is advanced and widely implemented, supporting renewable energy integration, stabilizing our power grid, powering our transportation, and finding application in various industries. Yes, there are challenges to overcome, such as improving efficiency, managing costs, and reducing environmental impact. But if we can tackle these hurdles, the potential of storing pressure could revolutionize how we store and use energy.